Good afternoon, and welcome to Learning with the Fosters, a beautiful, albeit very stormy day here in the beautiful island of Puerto Rico in Cabo Rojo, where Damaris and I live. So today's lesson will come from our house, as it's quite stormy outside. Today's the first lesson for Learning with the Fosters' series, If I Can Learn Math, You Can Learn Math, first course, Pre-Calculus, and this is the first lesson of that course. If you remember back to our introduction to pre-calculus, we mentioned that before we really get to the twin pillars of pre-calculus, algebra and trigonometry, we first are going to spend some time, I think some needed time, to either refresh on some fundamental principles or perhaps be introduced to, for the first time, some of these fundamental principles. And that's the journey we will begin today. We're going to take it slow. Damaris and I we have worked out a lot. It's been a big part of our lives. But recently, the last few months or so, in part due to Hurricane Maria, which ravaged through the island, and in other part to us just being extremely busy with quite a number of things, we haven't been in the gym lately. So we're back in the gym. So we're both a little sore. And when we go back, we don't just start lifting the same amount of weights, doing the same routine, or running the same amount of laps around the track. We certainly can't do that at our ages anymore. Rather, what we do is we work slowly back into it. Once we get in better shape, then we can get back up to our routine. But we pace ourselves initially. And that's going to be the approach initially with this course as well. We're going to pace ourselves. We will pick up the pace, we will pick up the tempo as we work ourselves into kind of the flow and some of the mathematics as we go. But the good news is we're going to take this slow, especially at the start. We're going to cover just a little bit of material in relatively quick amounts of time, digest it, do some simple homework. We won't get too involved with the homework for a little while, and allow us to kind of pace ourselves into really getting ready to putting our full minds and our full efforts into learning some exciting mathematics. So, let's begin. What are we going to talk about today? Well, we're going to be talking about sets, or basic sets, very basic set theory. This will allow us, among other things, to talk and think about number systems in more accurate, more precise, and really more meaningful and helpful ways, which will be important as we move forward in dealing with both algebra, trigonometry, and everything that's beyond. But sets and set theory are much more than that. They're very foundational to mathematics. They're also incredibly interesting. We won't see that in this course, pre-calculus. But personally, I've got a special place in my heart for set theory, as it, to me, is one of the most exciting, mind-blowing, profoundly confusing, and profoundly simple branches or areas of mathematics. We'll barely get a touch of some of what that is as our goal is to get ready to work with pre-calculus. But in essence, we can simply define a set, and we could be more precise, we could be more rigorous with this, but for now we'll simply define a set as a collection of objects. Now, we'll be a little more precise with our term objects. In dealing with sets, we refer to those objects as elements. My hand's a little tired from writing elements. That's kind of a long word. So, mathematicians, one thing I really like about mathematics is we like to abbreviate things. If we can assign a symbol to something or denote something in a much shorter way, we tend to do it. So this symbol here, that denotes elements. So when you see this, we're simply referring to elements. What are elements? Well, they are the objects that are of the collection, which we are defining as set. Now, if something's not an element, we want to be able to talk about that too without writing not an element. Again, that's kind of long. So we keep the same symbol and simply put a line dash through it. Our grandson, our oldest grandson, Yvonne, is at the stage, he's a first grader, where he's been drawing do not steal signs. In fact, he wrote one on our board a little while ago. He usually draws a person, he's actually a better drawer than I am, taking something. Stealing. What he does with that to say don't steal is he goes like this and puts a big X or a mark through it. Well, that's kind of the same type of thing that's going on here. If it's not an element, it's simply this symbol we're denoting as element with a slash through it. So, element, not an element. set is a collection of objects. Those objects we're going to call elements. Let's talk a little bit about ways to write or describe sets. The first way we're going to talk about is simply by using these what we call set braces, or maybe curly parentheses, or however you distinguish those on your keyboard from regular parentheses. But they're properly called set braces. So if we have a collection of objects or a collection of elements, what we can do is simply put those within these set braces. And this will write a set. So here's an example. Please ignore my misspelling here, I just noticed. Containing the elements, the number 7, the number 10, the letter or possibly variable J, the letter, possibly variable from the Greek alphabet alpha, and what do we have here? Oh, a nice little portrait of Dama. So our set consists of objects or elements, those elements being some numbers, some letters from 2 different alphabets, and a nice drawing of Damaris. Now those all could be variables, and by variable, again, we won't be too precise for right now, but we can simply say a variable in math very basically could be a symbol, usually a letter, usually from the English alphabet or the Greek alphabet, but it could be a picture of Damaris or a goat or anything. A symbol, usually a letter that stands for a number. And there's different types and aspects of variables that we'll talk about later, but for now, we'll keep it something like that. So if we want to, again, we don't want to write this whole sentence, the set containing the elements 7, 10, J, alpha, Damaris. What we can do is use our set braces to label that. So here we have the set containing the elements 7, 10, J, alpha, Damaris. Notice she's got cute little pigtails there. Alright, is that the only way to write this set using set braces? Well, it turns out no. We could also write it. There's nothing intrinsically important about the order in which these objects, these elements, are listed. We could simply label them as, again, within the set braces. We could put Damaris first. Of course, she's first. The number 10, the letter J, the letter alpha, the number 7, etc. We could arrange these in any sort of way. So the order doesn't matter to describe this particular set. Now the order can become very interesting and important when dealing with sets in other contexts, but simply to make a set, to describe this set of elements using set braces, the order doesn't matter. Okay, let's get even a little bit simpler. I don't feel like writing the sentence anymore. So customarily, the way we label sets are with a capital letter. Again, this could be anything. We could have this whole long phrase, or we could have a lowercase letter, or whatever. But customarily, it's a capital letter to label a set. Since set starts with S, we'll use S. So what we could say is S is everything that's in here. Well, I guess I won't be lazy. We'll write it out. Let's do a different order this time. Alpha, 10, J, Damaris, and 7. Did I get everything? Let's do this. Let's check. Let's count how many elements are in the set. 1, 2, 3, 4, 5. Let's see if we got them all. 1, 2, 3, 4, 5. Excellent. Did we repeat any? No, it looks good. A different order again, but it's still the same set. And now to save us time, instead of consistently referring to the set containing the elements, blah, 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 we can say the set S, or simply S equals, and then using our denotation of set braces, this is the set. So S is defined, S is equal to the set containing these elements. Let's pick an element. How about 10? We want to describe 10 as part of the set. So is 10 an element of the set? Yes, excellent. So what we could say is 10 is which one of these symbols? Yes, is an element of the set alpha, Damaris, 7, J, 10, again, remember order doesn't matter, or, my hand's kind of hurting. Let's do this. We can say 10 is an element of S. Now look at all the information we were able to contain within this, and look at how little writing we had to do simply by being familiar with the denotations. Notation is incredibly important, and this is something I've learned much later in life. Sometimes when you come to something new, a new subject, a new interest, you don't want to learn the terminology, you don't want to learn how to kind of the shorthand, but it really allows you to, first of all, communicate more precisely within whatever you're talking about. And also, in this case, it really allows you to compact a lot of very useful information accurately within a very limited writing strokes, which for me, that's a very good thing. Okay, so let's practice with this a little bit. Let's mix up a color here. We'll give a few elements, and we will use proper notation to say whether it is in the set S. So let's do -3. Let's do 164. And let's do, we're having fun with drawing. Let's draw one of our pets. She's a goat. Her name's Valentine. Kind of has sideways eyes, a smile, and she only has one horn. Damaris confuses her with a unicorn sometimes. So let's write properly whether these are, let's change this because we don't want them all to end up that way. Let's see whether these are elements within the set S. So -3, is that an element within S? No, it's not. So what symbol are we going to use? Excellent. So we can write, and let's practice saying, -3 is not an element of S. How about J? Yes, it is. So we can say J is an element of S. How about our goat Valentine? No, very good, estudiante. It kind of looks like Damaris a little bit, although Damaris is much prettier. But no, Valentine is not an element of set S. So, sorry Val, you are not. All right, not too bad, I don't think. We'll have a chance to kind of practice working on labeling, on denoting some of these in just a little bit. Okay, now, since we have a kind of a basic understanding of at least what a set is and some of the elements within it, let's look at a very limited number, but some of the qualities of sets. And for now, we're just going to look at 2. 1, a set can be finite. What do we mean by finite? Well, I think we all kind of have at least an intuitive idea of finite versus infinite. For a set, we can kind of briefly describe it as a finite set. It has a limited number, this little symbol, although not too precise, I'll use frequently as shorthand for number. It has a limited number of elements. So remember, each element is listed in the set, correct? So set S that we were looking at just a little while ago, that was a finite set. There was a limited number of elements, or the counting process, when counting those elements, 1, 2, 3, 4, 5, that comes to an end at some point. In that case, in that example, set S had 5 elements, namely 7, 10, J, alpha, Damaris. And again, not in any particular order. Let's look at an example. Here we have a set. We have the elements -3, pi, which we'll have fun with later, 7 and 3/4, or 3/4, a fraction. Well, these are all elements, so how many elements are there? 1, 2, 3, 4. This counting process came to an end, so this is a finite set. Not too difficult, I think fairly intuitive. Well, if it's not finite, then it is an infinite set, or the quality that we're looking at is there's an infinite number of elements. So a way we can describe that is there's an unending list of distinct elements. This differs from finite because for this example, okay, there's only 4 elements, it's fairly easy to see, but what if it's all of the whole numbers between 5 and 5 billion? Well, if we were to count all of those, that's going to take a while, so it can appear infinite, especially if you're doing it, but you know that counting process will eventually come to an end once we reach that end point. Well, in an infinite set, it's not so. There's an unending list of distinct elements. So an example, let's say A, and again, what would A be in this set, in this context? Well, we said that this is a customary way to label a set. So set A is the set of all odd numbers greater than 8. Let me read that again if you're having a hard time reading the board. The set A is the set of all odd numbers greater than 8. Well, let's begin to write this using our set notation we learned just a little while ago. So what we could say is A, because we don't want to keep writing all these words, right? At least I don't. A is, instead of using words, we're going to use our set braces. Okay, the set of all odd numbers greater than 8. So it's the first odd number after 8, 9. So 9, what would be next? Greater than 8, 11, 13, 15. Okay, wait a minute here. We're going to have to keep writing for a long time. This process will never end. It keeps going. So what we can do, here's another nice little notation device, is we can use, let's change colors, we can put 3 little dots or ellipses here. And what that indicates is that this pattern, which we've established, continues. It continues on. And of course, we need to end with our set braces. So these 3 dots, we can refer to as ellipsis points. And that simply lets us know that this process, every odd number continues on infinitely long. So this set A has the quality of an infinite set. The counting process will never end as we keep working, as there's always an odd number after that. Okay, talking about ellipsis points, we can use those handily for sets that are finite as well. Let's do an example. Let's say our set looks something like this. Okay, so we could write this out if we wanted. This set, it consists of 5, 6, 7, 8, establishing the pattern. Next would be 9, 10, 11, all the way up to 40. Well, we could write all those digits out, but this saves us some convenience, time, and space. So notice, just because there's ellipsis points doesn't mean necessarily that the set is infinite. In this case, it is finite. Our counting process comes to an end between 5 and, in this case, 40. But see how these ellipses really save us a lot of writing and a lot of space to do so. All right, excellent job. I'm very impressed. Damarius, you're really rolling on this. If you're having a hard time with this, this would be a good time to kind of pause, review everything we've done so far, as now we are going to look at another way to talk about sets, or to build sets. And this is called set builder notation. Simpler than it sounds. Set builder notation. Okay, a way we can describe this, and I think this will make more sense as we work through, but a way that we can describe it is set builder notation uses a variable to represent an arbitrary element of the set. All right, let's dissect this as we look through. Here's a way we can write that. I don't feel like writing this ever again in my life. That's a little too long. So a way we can abbreviate that is set. Well, in this case, we'll just use C. C is brace X. There's our variable. Long up and down mark. X is, and then I put in quotations, condition or conditions, ending with a brace. So what does this mean? If we were to read this, let's translate this into English. We would read this as C is the set of all elements X. All elements X such that X is, well, whatever conditions we put on it. So again, to read through this, and it kind of corresponds here, C is the set of all elements X such that X is whatever conditions or parameters are put on it. Let's look at an example. So C, we'll use this set builder notation. C equals, or let's read it out, C is, say it aloud as we go, the set of all elements X such that X is, here's our condition underlined in red, a counting number between 35 and 40. So let's translate this into a set like we were doing just a little while ago with our set braces. So we can write this, set builder notation. This will kind of put this in terms that we've been working with. Remember, we start with braces. Our condition is a counting number between 35 and 40. So we'll get more precise with what we mean by between in a few lectures. So between, does that include 35 and does that include 40? For now we'll say no, and we'll talk about more precise ways to deal with that in the future. But for now we'll exclude the endpoints. So a counting number, what is a counting number? Again, we're kind of building up where we can talk about numbers more and number systems more effectively. So a counting number right now we can simply describe as a number that we use to kind of count, or a whole number. 1, 2, 3, 4, not a half, not a third, not a negative. It's 1, 2, 3, 4, 5, etc. So a counting number between 35 and 40. So we're not using the n, so what would our first counting number be? 35 and a half? No, 36. So our set is 36. Is our first element. Does 37 is the next counting number? That fits within the range. 37, 38, and 39. Finish it off with a set brace. So, this is the more familiar way, as we've been looking at it, to what this set builder notation is saying. So, C is the set of all elements X such that X is a counting number between 35 and 40. Looks like this. C is set, the elements 36, 37, 38, 39. Not too bad, right? So let's look at this description a little bit more and kind of see where we get some of this. We won't delve too deep into it, but just a little bit. What this is saying is C is the set of all elements X. That's what this first part tells us. So it's using a variable to represent any arbitrary element of the set. So you can pick any element of the set, no matter what element it is, it will meet this condition. In case a counting number between 35 and 40. So pick any arbitrary element of the set, close your eyes, whoppity, 37, that is a counting number between 35 and 40. If it's not, then it doesn't belong in the set, as this next part demonstrates. So C is the set of all elements X, any element X that you choose, such that X is according to these conditions. I hope that clears it up somewhat. Let's look at another example. As we work through more of these, I think we'll see how it kind of corresponds. Next example, let's see D. You can see how creative I am. We're kind of going in order. A, B, C, D, sets. Set D is, let's read this properly. D is, help me out, the set of all elements X, such that X is, here's our condition, an integer between negative 33 and negative 29. So let's again put this in terms that are a little bit more familiar. So we don't have room underneath, so let's just say D is the set of all elements X. So any arbitrary element X in the set, if we pull out, what is the condition that it has to be? Well, an integer. What's an integer? Again, for now, we'll simply say it's a whole number and its negative counterpart, or its opposite. So in other words, 1 with negative 1, 2 with negative 2, 3 with negative 3, etc. Not a half, not a negative a half. So all those numbers, integers, we'll be dealing a lot with them. And we'll look at a way to kind of abbreviate that in the next few lectures. But it has to be an integer between negative 33 and negative 29. So we're not including the endpoint. So our next integer would be, correct, negative 32, negative 31, negative 30. And we get up to our endpoint. We're not including that. So how many elements are in our set B? 1, 2, 3. Is it finite or infinite? It is finite. And this is our nice little set in which our set builder notation describes. D is the set of all elements x, any arbitrary element x that we choose, such that x is an integer between negative 33 and negative 29. Okay, let's use some of what we've learned and kind of put it all together by looking at a few examples. We're looking at some of the qualities of sets, namely, are they infinite or finite, and are particular objects elements of that set. So we've got two examples here. Let's start with set B. So B is the set 23, 24, 25, our handy ellipsis, up to 106. So that the pattern 23, 24, 25, 26, 27, 28, 29, 30, all the way up to 106. That's set B. So let's look at these three proposed elements and properly denote whether they are a set or whether they are an element of set B or not an element of set B. So 77, would that be an element of B? Well, let's look at our pattern. 23, 24, 25, up to 106. 77, would that fit within set B? Yes. Excellent job, student Damaris. So how would we write that? 77 is an element of B. Excellent. How about 101? Excellent. Yes, it is. 101 is an element of B. Going to trick you on this one. How about 10? Give you a minute to think. No. Excellent job, because our set begins at 23 and works that direction, or in getting farther in the positive direction from 0. 10 is prior to 23. So how would we mark that? 10 is not an element of B. Great job. Let's do one more. Well, I guess, excuse me, first of all, is this a finite set or is this an infinite set? Great. There's ellipses, so that can be tricky. We might automatically think infinite, but it's finite. There's a definite beginning, definite end, and our counting process as we count the number of elements within it will certainly come to an end. So this is a finite set. Very good. Let's look at this. Set C. So C is the set negative 10, negative 9, negative 8, ellipsis. So the pattern continue to be. It's again increasing, growing. So negative 10, negative 9, negative 8, negative 7, negative 6, negative 5 will eventually cross over from 0 into the positives and out towards infinity. Okay, so 30. Is that an element of C? Yeah. Wait, I'm confused though. In here there's only negatives. How could a positive be an element of C? Well, excellent observation. The set continues, it grows. So eventually it will include 30, as our ellipses let us know. So 30 is an element in C. All right. Our next one, negative 20. No. Well, you're right, but I'm a little bit confused again. 20 is pretty big in the negative, so shouldn't this be included in the set? No, because this direction, nice thumb point. Yeah, negative 20 on a number line, which we'll be spending some time with in a few lectures or a few lessons, is getting farther away in this direction. So negative 20 is not an element of C. All right. How about 1? A very important number. Is 1 an element of C? You got this. I think we're ready to move on. 1 is an element of C. And one more thing is, what's the quality? Is this an infinite set or a finite set? Infinite. Very, very good. And why? It has ellipses just like this one. The pattern continues. We can keep writing the next elements, but that counting process, when we go to count them, will never come to an end. We can always write one more. So this is an infinite set. All right, we're just about there for today. We're going to do a few more examples and put together some of what we've learned, and then it's homework time. And we'll talk about that in just a minute. So, first example. E is, remember our, let's read this out as we should. E is the set of all elements x, such that x is, our condition, an integer greater than negative 650. So our question is, well, we've got 3 questions. We've got 3 possible elements here, 3 numbers. Our goal is to decide and properly denote whether they are elements or not elements of E. So 3. Well, before we get too crazy, let's describe this, let's write this, if possible, in using set braces so we can kind of see some of those elements together. So let's have that be our first task. We can do that over here. So E is, okay, an integer, we talked about that just a little while ago, greater than negative 650. So a number line, negative 650, not including 650, or negative 650. The next object up would be, because it's greater than, moving towards the positive direction, negative 649. Okay, what's the next integer? Excellent, negative 648. And we're running out of board space. And man, my hand's really tired. So what will we do at this point? You should have at least 3 elements listed to recognize the pattern, but we won't in this case. We'll put our ellipses on. This continues onward. So first question, excuse me, what is this an infinite or finite set? Excellent. Infinite set. It continues on infinitely. So now that we have another picture, we can look again kind of at these possible elements. 3. Is 3 an element of E? Well, 3's to the positive side. It keeps moving closer. It's infinite. It'll eventually get there. So very good. Yes, 3 is an element of E. All right, let's look at negative 427. What do you think there? Yeah, very good. It is as well. It's a negative number. It's fairly a large negative number, but it's still, you're going to negative 649, 648. You're eventually going to come to negative 427. So negative 427 is an element of E. All right, how about negative 1,000? Well, the numbers keep getting bigger. It seems like it should be, but wait a minute. Nope. That is on this side. We're moving that direction. So negative 1,000 is not an element, whoppity, of E. Okay, very good job. Let's look at our next example. Here we have F. F is the set of all elements X, such that X is an integer between 1 and 10. Okay, we're kind of getting good at that. We can deal with that. But wait a minute. And even, an even number. So here we have 2 conditions. So any arbitrary element X that you choose out of the set has 2 conditions to be part of set F. It has to be an integer between 1 and 10, and it has to be even. So let's put this in terms of set braces. Our first element, let's deal with our first condition, an integer between 1 and 10. Well, let's just list those. Between, we're not including the endpoints. So 2, 3, 4, 5, 6, 7, 8, 9, we've reached 10, that's the end. Okay, we dealt with our first condition. But if we were to choose an arbitrary element x, let's say 7, it meets the first condition, but it doesn't meet the second condition. Why? Because it's not an even number. So our set F needs to, and I should label this as F, let's cross out, according to the second condition, it has to be even, so let's cross out all of our odds. All right, that leaves us with set F is the elements 2, 4, 6, and 8. Okay, so how many elements are in set F? The set of all elements x, such that x is an integer between 1 and 10, and even. There are 4 elements. Next question. Is F infinite or finite? Finite, fairly obviously finite. In fact, our counting process comes to an end quickly. 1, 2, 3, 4. Excelente. Uno más example. One more example. We're looking at set G. Okay. G is the set of all elements x, such that x is an integer, abbreviated, less than 33, and divisible by 2. Okay. Let's attempt to put this, first of all, we've got how many conditions again? It is an integer less than 33. Okay, there's one condition, and divisible by 2. Okay, let's deal with our first condition first. X is an integer less than 33. So 33, 32, 31. Uh-oh, our process can go on and on, right? So we use ellipses, and it is therefore, it's an infinite process. It's going to keep going in that negative direction, and each element is also divisible by 2. So I won't bother writing this. Let's just simply look at the elements. Let's compare each condition. Is 10 an element of G? Well, is 10 an integer less than 33? Yes, it is. And is it divisible by 2? 10 divided by 2 is 5. Yes. And by divisible we mean there's no remainder over. So 10 is an element of G. Excellent. How about 50? Is 50 less than 33? No, it's not. It is divisible by 2, but it's not less than 33, so it doesn't meet both conditions. So therefore, 50 is not an element of G. How about negative 3? Well, negative 3 is less than 33. Condition 1 met. Condition 2, divisible by 2, evenly divisible by 2. No. So negative 3, again, meets one of the conditions, but not both. Therefore, it is not an element of G. An arbitrary element x does not meet both of those conditions. How about negative 1,000? Negative 1,000 is less than 33. Check mark. And is it divisible by 2? Yes, it is. So our last one, negative 1,000, is an element of G. All right. Great work, everybody. I'm very impressed. You guys did very well on this. We'll continue our discussion with set theory for the next 2 lectures. We won't get too deep, but we're going to take it slow. We're working our way into the pace here. But it's important, as we looked at today, to understand some of the basic notation for set theory, some ways we can talk about it and describe it, some shorthand, which really helps out. And we also looked at some of the qualities of sets, namely infinite or finite, and also elements, what it means to be an element, and some ways in which we can look at that. Now, the next step is homework. Okay, now is the time where real learning takes place. As I mentioned before in the introduction, when you go through and do homework, finding out what works and finding out what doesn't work and seeing different problems is, at least for me, where much of my math learning really took place. The homework time. But also remember, we're pacing ourselves. We're getting into this. So our homework assignment is brief for this lesson, and I don't think too difficult. A few may make you scratch your head a little bit, but I don't think it's too bad, and it's fairly brief. We'll elaborate as we get on with the courses. But here's your homework. Identify each set as finite or infinite. Secondly, determine if -2 and 7 are elements of the set. So 2 parts. We have 5 problems, 5 different sets to look at, 5 different sets to both identify as finite or infinite, and 5 different sets to determine if -2 and or 7 are elements of the set. Look forward to seeing you next time as we work through each of these together. So do this on your own, then we'll get back together and we'll work through each of them and see how we can do. Have a great time. See you next lesson.
Thank you for learning with the Fosters. This is a friendly reminder. Remember that these courses are not for free. For information of the cost of the lessons and how to pay, please visit our website. Thank you so much for being with us.